It's showtime! Sorry. Hey guys, it's nice to see you. Lockdown, I'm telling you, it's what it's doing to me. It's what it's doing to me. Look at this. This is awesome. I turn up to class dead on time and everyone is there waiting for me. You guys are just the best. Oh, you guys are awesome. I love you guys. Right, let's do the register and then we can smash on with acid-base theory. It's so lovely to see you all. Did you guys all have a lovely long weekend? I hope you did. Hope you all enjoyed yourselves. So let's see who we've got here. I think, look at this, got everyone. Hola, ¿cómo estás, Imani? Imani's in the house. Do I have Zach? Got a feeling I'm gonna have Zach. Where's Zach? No, Zach! Ah! Oh, have I got Sophia? I'm having to hop between laptops. Do I have Tiffany? I've got a feeling I've got Tiff. I'm sure I've got. There's Tiffany. Yes. Do I have Kayla? There's Kayla. No, Zach. Somebody message Zach ASAP. Kayla was like it. Zayla. Wow, just blended two names. Mel. Do I have a Mel? I'm sure I've got a Mel. Where's Mel? There's Mel. Mr. Duncan. Is that shirt from Timberlands? I think I have the same shirt. Do you know what? I actually don't know. It's just a Top Gun one. My sister bought this for me like a million years ago. Got Audra. I'm sure I've got Lara. There's Lara. Do I have Atia? I've always got Atia. Where's Atia? Hey, Atia. Do I have an Anya? Where's an Anya? Ananya? Where's an Anya? No. Oh, there she is. Hi, Mr. Duncan. Also off topic. I've got such a bad headache. Oh, Ananya, you can always watch these YouTube videos back later. If you're feeling like you're not feeling very well, go and lie down. You can always watch this back later. Do I have Caitlin? I think I've got Caitlin. Where's Caitlin? Spot Caitlin. Where's Caitlin? Have I got no Caitlin? Where's Caitlin? Caitlin! Sup, Zach? Zach's in the house. Caitlin, how are you, Caitlin? Caitlin. I've got no Caitlin yet. Oh, there she is. Do I have Dom? I saw Dom. I saw his. Oh my God, the goatee. Oh no, I forgot about that. It's the most. Dom, can I ask, why is it the most wonderful time of year? Like, is there any reason behind that? Where's Ryan? Where's Ryan? I can't. There's Ryan was in. Ryan Goodman, you were in first. Thanks. Yeah, I'm sorry about the beard, folks. It's locked down. That's all I've got. That's it. Quarantine goatee. Yeah, I know. Because it's another Mr. Duncan lesson. Oh, Dom, you're a legend. Thanks very much for that. That's what's really made my day, that, Dom. Yeah. Guys, we've got a full house. We're done. Yeah. Doing the chemistry dance. Chemistry goatee dance. Oh, I've suddenly realized this is live on YouTube. Never do that again. Oh, no. I've lost my mind. Right, guys. Acid is the most. Right, guys. Let's crack on. Share screen. Look at this. We're straight in. Boom. So we're doing acid base today, folks. Doing acid base. Okay, I think I'm all ready. Look at this. I'm all ready to go. So, okay. So last lesson, do you know what? Feels like ages ago, doesn't it, folks? Like the last lesson, what we did is we did a bit of recap on the kind of acid-base stuff that we did in year 7. You guys were all massively upset about how much we had lied to you. Can I just point out, I didn't lie to you. I realized this after the lesson. Like, you guys were like, you lied to me. And I was like, no, I didn't even have you in year 7. Although don't tell them, but I did lie to my year 7s. But I definitely didn't lie to you. Like, it had nothing to do with me. Oh, good times. Okay, so we've got 3 learning objectives today. So we're talking about the word dissociation today. That's my main focus. 3 learning objectives. One, I want you guys to understand the dissociations of acids stroke bases. I should have put that in there. I apologize. There you go. So the dissociation of acids and bases. And really, it's my job today is to get you guys to see that word and understand exactly what it's saying. Yeah. Write dissociation equations and then to understand the term weak and strong. So those are my outcomes today. That's what we're going to focus on. So the first thing is the word dissociation. So my wonderful, wonderful year 10s on the chat, please. Can somebody tell me what they think the word dissociate means? So definition, it's the first thing we need to do. Define. Yeah, we need to define the word dissociate. What do people think that means? Yeah. Now, whilst you guys are busy typing on the chat, I know that there's the delay, so try to fill it as much as I can. Obviously, usually I'll do it with like some big rambly chat. I hope I've spelt the word dissociate right as well. Not associated. Ryan, you're so correct. It means not separate. Yes, Laura, to become detached. Yes. Oh my God, that's awesome. Yeah, it means to separate. It means to become detached. Used to be together, but not it's apart. Split into small atoms. You guys are awesome. All of those are perfect. Yeah, those are great. Not associated. Yeah, the word dissociate. To split into smaller units. So the key thing here is the splitting. Now, some students then commonly say, I've seen something similar to this. Yeah, I've seen something similar, which is I've come across the word thermal decomposition. Yeah, to break up using heat. Yeah, to split into smaller units using heat. Well, the word dissociate means to split into smaller units. And it usually means in the context of being put into something else. Now, you don't need to know that. You never really go into the depths of the differences between things like decomposition and dissociation. But to split into smaller units, and I can add this is not anything you need to worry about for your exams. You will never need this for your exam. But I always like giving that extra bit of information. To split into smaller units, when put into I'm gonna give the example here of a solvent. Yeah. Now, can I just say that the important bit here is the split into smaller units. That's what it literally to break apart. Yeah. But because we have other words for this, decomposition. The word decomposition, so define, it's nice to remind ourselves of this. Yeah, decomposition. To decompose means to split, which is the same as break up, to split into smaller units. Well, that's rather bizarre, isn't it? Yeah, students don't like that. They're like, whoa, it means the same thing. But the word decomposition means to split into smaller units, and there's a ... here, because there's usually an explanation to what's causing it. So, for example, by heat. Yeah, what that means is the decomposition then actually becomes thermal decomposition. Yeah, but the word decomposition means to break up. The word dissociation means to break up, but in this case, when put into a solvent. So what I'm trying to do is, I'm trying to say that this one here is context. This here, the word dissociation is given in chemistry, yeah, in terms of acids and bases. Because we've got so many of these words that are so similar. What we needed to do is we needed to give these other words that people would associate. Oh dear, I shouldn't use that word in the explanation of the other word, which people would link to topics. So dissociation is linked to acid-base theory. So let's now have a look at what this actually means in terms of acid-base. Now, the first thing I need to now do is just really quickly say, okay, so we put a little subtitle of Dissociation. Can someone do me a favor, year 10? Is that the correct spelling of dissociation? Can you guys just confirm that with me? And I'm going to put a slash of ionization. Right. So I need to explain this because in acid-base theory, both of these words mean the same thing. So the first thing I need to do is just go same thing. However, chemists realized, yes, well done. Thanks for that. Thanks, Alping. Thanks, Sophia. You guys are stars. So these two words were both used. And what they realized was that they would prefer the term ionization. The reason being is it gives you more information. Yeah. The word dissociation now gains this term ionization because it describes the particles that are now produced. Now, people say, why do you teach both? Why don't you just teach ionization? I have to teach both because both are used by the exam board indiscriminately. They just move between the two. Yeah. So I have to tell that these both mean the same thing. And now we need to put this into context. So we know in reality, all this means is split up. That's what this means. Yeah. So what we now need to do is look at this from an acid perspective. So let's split up some acids. Yeah. Let's go for our favorite, e.g. HCl, hydrochloric acid. Now, by the way, I'm going to love this because guys, we have done calculations. We have done bonding. First question, bonding. Sorry, bonding? What bonding is this? So what bonding is in HCl? And what we're going to do now is we're going to split it up. We're going to dissociate it. We're going to split. Now, this word is given very distinctly to acid bases, and you're about to understand why they preferred, why the term ionization then made an appearance. By the way, dissociation came first, ionization came second, but ionization came as a result of their newer understanding of what was being produced. So what we realize is happening, so I'm still waiting for people to give me the answer to the bonding question. What is the bonding in hydrochloric acid? Yeah, we're going to now take hydrochloric, by the way, and I need to be really careful here. There's detail here I've got to be really careful of. Well done, Laura. Great job. Well, spot on. It is correct. It is indeed covalent. Yeah, which means we've got hydrogen and we've got chlorine, and they look like this. Yeah, there we go. So there's our and this is where I've got to be careful because I was calling this hydrochloric acid, but in fact, of course, it's not. Yeah, I know this is a nightmare. Please forgive me, but this is one of the few ones at Excel you got to know. HCl gas is called hydrogen chloride. It is not an acid yet. Because the first, and this is going to be a nota bene, which nota bene, got to say with that French accent. Simple covalent, love that, Dom, absolutely spot on. I even really love you adding in that word simple that the others didn't. That's great. Yeah, it's nice. I always like that word simple just because I know that covalent means simple, but some people forget the fact that simple and giant are separate, but covalent simply means simple, and I love that. It's good. So nota bene, an acid slash base are not, capital letters, are not acids or bases until in water, brackets, aqueous. There we go. So that's isn't it Latin? Yes, it is. It is Latin, absolutely. Nota bene. Like that, I believe. Somebody check me on that. It is Latin. And in Latin, that means important notice. Yeah. So if you went to the beach in the old ancient Roman times, yeah, on the beach would be signs that says, nota bene, don't swim here, sharks. Yeah. Oh, double N. Ooh, double N. Like that. Then nay. Oh, that makes sense. Wait, it isn't. Oh, you've ruined it for me. It's with one N, isn't it? I didn't think it was, but yeah, no, yeah, found this one. Okay, so acids, we realize, single N. What that means is, for an acid to be an acid, it must be in water. Otherwise, you give it its chemical name, hydrogen chloride. We see this, of course, in that demonstration with the hydrogen chloride and the ammonia and the formation of the white ring. Whoops, sorry, but it looks better with two. Love it. So, okay, what we're now going to do is going to take the HCl gas, and by the way, it is a gas, a colorless gas. I'm going to take this colorless gas, and I'm going to add it to water. Add to, I'm just going to put H2O. Add to water. And something really cool happens. What happens is, poof, it splits. That's what it splits into. That there, this is dissociation. Dissociation. Can everyone now see the word dissociate means to separate? The particles have separated. But can everyone now also see why it's now called ionization? Because we're producing ions. Now, can I just point out, by the way, there is so many little these tiny little nuances in chemistry which do cause trouble. The word ionization is a bit of a nightmare because ionization is used somewhere else in A level. You'll see that later. When you get to A level, you'll see it. But both those words in this subject mean we can interchange between them. It makes no difference. But we can see why they're ions. They are ions because the H becomes H plus and the Cl becomes Cl minus. And it's nice to mention conservation of electric charge. We know, I'm just going to quickly mention this. This is a physics rule. This is just something useful that I only started adding to my lesson relatively recently. It looks like I've got double V. Conservation of electric charge. So when we balance equations, we know that what goes in must come out, in terms of atoms. But there's also conservation of electric charge, which means if I put in AB and we know this has no charge, we know this, it looks like no charge. No charge, that still looks like Darge. This has no charge because there's nothing, no number there. If I were to split this into A and B, A is positive and B must be negative. Because on both sides of the equation, on both sides, it must add up. On this side, no charge. On this side, no overall charge. The 1 plus cancels the 1 minus. That's actually really important. It makes everything a lot easier when you start looking at this. So the HCl splits up to form H plus and Cl minus. And here's the important bit. Here is what makes an acid an acid. Acids give off H plus in water, and that H plus is what attacks you. It wants electrons desperately, and it's going to take them from you. So let's do another one. Let's look at another example. Okay, e.g. number 2. Now you guys are gonna have a go at doing this, and I know it's on the chat. It's a bit complicated, but we'll do our best. So let's do HBr. Gonna take HBr gas, which is hydrogen bromide. I'm gonna add it to water. Add to water, to H2O. And what am I going to get, folks? Can you guys on the chat complete the equation, please? You can even include state symbols if you wish. I realize I probably didn't up here, did I? No, H plus aqueous and Cl minus aqueous. So what am I gonna get if I put hydrogen bromide into water? On the chat, first person, see who's in first. One of the best things about, hey, Laura, smashed it, well done. Sophia, well done, great job. Absolutely right. Is spot on, Laura, well done. you're going to form H plus aqueous and Br minus aqueous. And this, so this here is called hydrogen bromide. Hydrogen bromide, but in water, HBr aqueous is called, God, I wonder if you guys could get this. Is the arrow always presumed to be adding to water? Yes, Dom, great question. It is. In dissociation questions, you just show that it's this in reality, Dom, you'll never write that down. Wow, Sophia, well done. You ledge. That there is hydrobromic acid. Have I said that before? Sophia, how did you know that? Atia, well done. Spot on. Hydrobromic acid. Do you want another one? Let's do another one. EG3. So I'm going to add HI, gas, to water. But isn't it just hydrochloric acid? Do you mean the fact that you got it from... Yeah, but they're not the same words. Like, you've done great. The translation is correct. Absolutely. Using logic, it should be hydrobromic. All right, Atia, tell me that one. What's this one here? Is hydrogen iodide. What's the acid called? Impress me. HI aqueous. Go on then. Darn it! Everyone knows it. Oh, Ipshita. Hi, it's so nice to see you. Thanks for coming. Guys, everyone say hi to Ipshita. Ipshita is a student in the UK who I helped a bit with her chemistry, and she comes to my webinars. Well done, guys. It is. It's hydroiodic. Hydroiodic acid. And I form H plus aqueous and I minus aqueous. So we realize that all the acids, oh, it's so nice that you guys are all so lovely. Hi, Ipshita. It's so nice to see you. Ipshita, I gave you the calculations test that I gave my year 11s, and you didn't. Did you have a go at it? Did you have a go? Let me know how you got on. I didn't get your result. I just wondered whether or not you'd had a go. Oh, it's so nice. Everyone's so welcoming. You are always welcome to come to my webinars, Ipshita. It's lovely. Okay, guys, impress me. Right. EG number 4. Right. Uh-oh. It's all right. It's all right. Okay, guys. Can everyone complete the equation, please? What am I going to get when I put hydrogen nitrate? And by the way, it's actually a liquid. Yeah. Hydrogen nitrate. By the way, this actually has another name because it's special. Yeah. This one is otherwise known as, oh, what a mess that was. Otherwise known as concentrated. I know it's weird. Lara, yes, I did, but I did it on paper because I have a super dodgy Wi-Fi and then watched your webinar. Well done, Ipshita. How did you get on? Out of 20, what did you get? This is called concentrated nitric acid, given a special name. The word concentrated means without water. It comes in later, but well done to Lara. Spot on. 17. Ipshita, well done. Great job. I have a second one if you want to have a go at it. So just as Lara said, spot on. We're going to get H plus and NO3 minus. So it's breaking in half. Do you know what I want to do now? I just want to show you this as a picture. So here's what's going on as a picture. Got some water, some water. Yeah, I've got my hydrogen chloride, which is here. Hydrogen chloride, gas. And I put it into the water and poof, it splits. It's just nice to show you guys as particles what's going on. Now year 10, you guys know just how much I value you. Oh no, Helping's just done it. He's just done it. Helping, you're nearly there. Right, guys, I'm letting you guys know now that I am giving you, no, hang on. Right, I'm going back to video. Right, year 10, I'm not fibbing to you. What I'm just not doing is giving you the full picture. The next time you're going to come across acid-base theory is in year 13. Yeah? I know Laura's doing that. Okay, so I can tell you the real story, but I need you guys to be able to filter. Yeah, remember that there are times when I teach you A-level and times when I teach you GCSE. I need you guys to be very aware of this, and you are quite happy completely at this point. Everything I have taught you is good. That is, can I just point out, and I need to reinforce this, betrayal. No, lie after lie. Dom, stop it. What if you gave us the full picture anyway? All these lies. No. Oh, it's you guys. Sometimes I wish you guys were just here because it would just be so much easier for me to talk to you. Right. It's not a lie. This is still important. I need you guys to have this. Yeah? We treat acids and alkalis like this because, okay, all right, fine. Okay, look, I'll just do the real thing. Okay, so the real story is more than this. The real story is what's happening is this. The hydrochloric acid, the hydrochloric acid, the problem is if I'm going to do this properly, I need to draw this out properly. And right, the hydrochloric acid looks like this. Hydrochloric acid looks like this. When you add it to water, Mr. Duncan, you forgot to switch back. No, I did. Sorry, there we go. The hydrochloric acid looks like that. Everyone agrees. His nostrils. Ugh, fancy light, I know, right? Right, here's the hydrochloric acid before as a gas. I'm now going to also show you what this looks like with a bond. It looks like this. Would everyone agree? Yeah, this is the dot and cross. This is the Lewis diagram. This is the Lewis dot / cross diagram. This one here is our stick diagram. We use them a lot. Yeah, this is a stick diagram. So what now happens is that when I add this to water, the water attacks it. Because what does the water look like? This is where I've got to be better on my board. Water looks like this. Each oxygen atom has 2 H's. Yeah, circle, 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 circle. So everyone here would agree that the oxygen has made the 2 bonds. Yes? But here's the problem. These guys are going to collide. And the water molecule is going to steal the hydrogen. It's going to steal it. Let me show you this in terms of sticks. It's easier to follow with sticks. One of the electron pairs on the oxygen has 2 electron pairs. One of them will attack the H. And that bond here, this bond here, must break. And it'll go back in that direction. The electrons in this bond will go back to the chlorine. So in reality, what's actually happening is this. This is the real picture, guys. Now, you do not need to know this. You do not need it. Yeah? Oh, you do not need to know this. This is A-level year 13. That's the real picture. Now, can I just point out that the people often ask at this point, so why do you teach the other one? Because the other one is needed. The other one is used. Yeah, because in reality, H3O plus is just that. That is the real picture of what H plus doesn't really exist. It's H3O plus because you have to have water there. H plus must be stuck to somebody, but it doesn't really like it. It wants to come off. So we treat it as H plus. Yeah, just to let you know, by the way, that this here is not a dissociation equation. Yeah, this is the Bronsted-Lowry equation, if anybody's interested. This is year 13. This is the Bronsted-Lowry. I'll explain that because Bronsted-Lowry, two people, Lowry equation. This I will explain to you guys. Do you know if we were in class, I would just teach you A-level properly. I'd just do it all properly. Yeah, I'd have no issue with doing that. But in reality, you will never at year 11, at GCSE, you will never need H+. You don't need it, so don't worry. But you do need to be able to do these dissociations. These appear at A-level as well, by the way. They do appear. Right, let's do a harder one. Now that you guys have accused me of lying to you and let's do the next one, number 5. Right, guys, H2SO4 is going to dissociate when added to water. Add to H2O. What am I going to get? Go. That's a liquid, by the way. Concentrated sulfuric acid. Guys, impress me then, year 10. Impress me. What am I going to make? Ipshita, beat them. Get on the chat first. Show them that you know what that's going to make. Lara, no, not quite. But nearly, very, very nearly. You didn't balance the equation, Lara. But you're nearly there. Laura has given you, Amani's in the house. Boom. Amani smashed it. So let's show you what this looks like. Sulfuric acid looks like this. This is what sulfuric acid actually looks like. Crazy or what? This is sulfuric acid. When you put sulfuric acid into water, it splits. And I will get 2 H pluses and SO4 2 minus. I'll draw it out properly. If I'm going to draw it, I may as well draw it properly. Yeah, there we go. So the equation, that's the picture, the equation becomes 2 H pluses and SO4 2 minus. Do you notice my math school have failed me yet again? Oh, Atia, it's just basic maths. It's not complicated. Do you notice on this side of the equation, 0 charge? Yeah, 0 charge. On this side of the equation, I now also have 0 charge because I have 2 plus from the hydrogens, because there's 2 of them, and 2 minus, so it cancels out to give me 0. 0 charge. It's really handy. Mr. Duncan, what about H plus and HSO4 minus? Dom, well done. Really, you're asking such great questions. I love you guys in year 10. You guys are just the best class I've ever taught. You guys are amazing. Dom, great question. So Dom, would you agree? I love what you've done. You've looked at the, you've remembered an ion that I taught you guys, the hydrogen sulfate ion and the hydrogen carbonate ion. Dom, when this splits up, technically it would actually happen in a 2-stage process, but the process is so fast, you'd never see it. Yeah. In order for you to actually capture the HSO4 minus ion, you'd have to actually add a correct amount of moles of a base to neutralize just half of it. It's a great question, Dom. You've done some amazing, honestly, that's way beyond your level. It's a great question. What will actually happen, it will do it in a 2-stage process, but the process is so fast that you can't capture it. It's instantaneous. Yeah, it's just so rapid you can't capture it. Yeah, but it's such a great question, Dom. But in reality, it is doing that, but so quick you couldn't hold it. It would just go poof, poof, straight to that, and you wouldn't stop it. Great question, though. Great question. The hydrogen sulfate ion. That comes in later on, but that's a great question. So we now recognize. Do you want one more? Do you want one more, folks? One more. Oh, if I give you one more, you're not going to like me. Okay, one more, folks. EG number 6. Right. Guys, what am I going to make? And you guys are all going to go, that's easy. Off you go on the chat. Would anyone like to tell me the name of this guy, please? That, of course, is hydrogen fluoride. Everybody knows that. But the question is, what's it called when it's in water? Who's going to be first? Who's going to be first? I love this game. I quite like the delay because it gives people time to think. Like, I'd love to think that you guys are doing what I'd imagine, which is you all having a think about it. Look at that. Laura's in there. Amali's in there. Nailed it. Spot on. Look at that. You guys are awesome. I love that. Lynn, you swapped the O and the U over to make it Fluoric. It's amazing. Do you know that I have to, in order to remember to spell fluoride or fluorine, I have to remember the word flour and then remember to flip the O and the U. Isn't that stupid? This is Hydrofluoric. Now, any of you, let's see, I'm actually pausing because I forgot how to spell it. Hydrofluoric acid. Right, if any of you guys watch Breaking Bad, you probably shouldn't. It's horrendously gory and you shouldn't watch it. Terrible TV program. This actually makes an appearance, hydrofluoric acid, in the TV show, and it's completely wrong. Absolutely wrong. Meth. Yes, Ryan. Brilliant. Well done. Yes, it is all about making meth. Yes, crystal meth, yeah. And in the show, they want to dissolve somebody. They've killed someone, they want to get rid of a body. So they say, oh, let's use hydrofluoric acid. No, I don't think so. Yeah, that is not correct. The reason being, and I'll explain why now. Number one, hydrofluoric acid is really scary. The only people who have access to it are dentists. And they have it locked away in like a triple locked safe. Scary stuff, hydrofluoric. Eats everything. Especially likes bones. So before I go into the gory details, can someone tell me what I'm going to put here and here, please? Just on the chat, really quick. What am I going to put there and there? Thank you, Hao Ping. Spot on. I'm going to put H plus, aqueous, and F minus. Now this equation, no, Sophia, looks like it's time to become a dentist. Sophia, can I ask you, can you do me a favor? No, Dom, do me a favor. Can you just delete that? If you're gonna, oh no, this is why. You wonder why we lied to you. That's why on the chat, especially when you guys wind me up. The evil hydronium ion. Wow, Dom, how did you know it was called the hydronium ion? Did you just Google that? Nice. Nice. Oh, it's just nice. I thought it said noise living. It's amazing. It is the hydronium ion, right? Right. Now, guys, here's the bit you're not going to like. We need to edit this in our books because that arrow there is not correct. This is the correct arrow. Can anybody on the chat please remind me, nota bene, what does this arrow mean? What does it mean? What does it mean? Lost my marbles. Thank you, Amani. She is on it today. It's reversible. Whoop, whoop. It's reversible. So it means that the reaction can go both forwards and backwards. Oh, Hao Ping was in there first, but he spelled reversible. It's reversible. So what does that now mean? It means the elements are indecisive. Oh, that's amazing. Libby, I love the fact that you're giving these elements and these atoms like personalities, like they're going, I don't know which way to go. I'll go back that way. Oh no, maybe I'll go that way. It's amazing. Love it. So it's reversible. Right, guys. So first thing, let's go back to our learning objectives. Everyone here can do this one now. The dissociation, whoops. Everyone here can do the dissociation of acids. So let's now just check that everyone can now do the dissociation of bases. By the way, we can also do writing dissociation equations. Let's put this into a base setting. Let's put this into a base setting. I'll change my color back to black. So if we can make a quick nota bene, love my nota benes. Nota bene, H plus is acid. Yeah. So if you ever see this in an equation, yeah, if you ever saw, this is where I need to be really careful here. I'm going to give an equation that you guys aren't going to like very much. Oh no. Cr2O7 minus goes to form Cr04 2 minus. Balance the equation, 2 chromiums, 1 water, 2 H pluses. There we go. So this equation that I'm just giving you, this is just the notabonic acid is H plus. Yeah. What that means is if I see this in an equation, back to black, I know, right? That there means acidic conditions. It means that if I want this reaction to happen, acidic conditions, people go, I don't get it, in acid. Yeah. Do this in acid is what it means. It means that in that beaker, acid must be there. If there's no acid, it won't happen. Yeah, it just tells you something about the reaction. It means in acid. So if you ever see this, you think to yourself, acid. Yeah. Now we pick up the next one, which is basic. So let's do dissociation. Dissociation of bases. Right, number 1, NaOH. Right, this is sodium hydroxide. I'm going to put it into water. This is a solid, by the way. It's a white. What type of bonding is taking place in that, please? What type of bonding? And then what ions am I going to get when it goes into water? Add to H2O. What am I going to get? Well done, thank you, Hal Ping. Smashed it out of the park. Great job. It is indeed ionic. Yeah, it's an ionic, hence why it's a solid. Thank you. Thank you, Atia. Lara, well done. Great job. Spot on. I'm now going to get Na plus and notice my change in color. And OH minus, which I've done in purple. Can someone tell me why I have done that in purple, please? Why burble? Question mark? Well done, Sophia. Well done, Lara. Great job. Spot on. Why purple? Let's go for another one. Let's go for number 2. Let's go for calcium hydroxide. What am I going to get when this goes into water? Purple alkali, well done. Base, alkali, alkali, base. Tiffany, well done. Laura, Atia, Amani, Sophia, great job. Yeah, purple, universal indicator. Yeah, we've got purple, universal indicator is purple indicator. Yeah, purple because it's an alkali. I like it. Cool. Because its pH is above 7. Well done. So, guys, what am I going to get now here when I put calcium hydroxide into water? Add to water. Ah, Amani, think about it. Where's that 2 on the calcium going to go? Lara, well done. Sophia, outstanding. Well done. You guys are awesome. We're going to get calcium plus 2. Why is it plus 2? Because it's on the periodic table. It's in the plus 2 section. We know this. Calcium's in group 2. Yeah, if calcium's, this is, we all know this. By now we've been doing this, say, plus 1, plus 2. And there's calcium. So I'm going to get calcium 2 plus and 2 OH minuses because of conservation of electric charge. Yeah, the charges cancel out. On this side, I have no charge, no overall charge. I know it's no overall charge. On this side, I've got plus 2 and 1 minus times 2 because I've got 2 of them. So I've got 2 minus 1 times minus, yeah, minus 1 times 2, that's correct. And then so minus 2 plus 2, it cancels out to give me no overall charge. Conservation of electric charge is so handy. It's always got to be there, always. So there's our equation. The dissociation, and of course we now see this, and as soon as you see that, you think alkali. Now, that, by the way, is actually true. Yeah, we know that OH minus in water means alkali. We know that base, it should use the correct word /base. Yeah, but that is going to be aqueous, which means it's also an alkali. So that is also true. Yeah. So these dissociation equations are tricky just because of these numbers that you've got to remember to add up. Is there a difference between a strong and Dom? I'm just about to get there. So let's go back to my learning objectives. We can now do, all of us can now do that one and that one for alkalis. Right. So strong versus weak. Let's do a new title. Okay. So strong. It looks like I put strang. Strong versus weak. So, Dom, maybe you can answer your own question. So there are definitions. So can I just point out in year 7, they lied again. I'm sorry, guys, I lied to the year 7. So I can't talk about dissociation and equilibriums with them at year 7. Their poor little brains will explode, and then there'll be blood and brains all over the walls, and it's really hard to clean up. I can't do it. I have to lie. I'm sorry. So what does so a strong, let's do the question. Question. A strong acid. What does the word, it's okay, year 7 deserve to die. Oh, to be lied to. Oh my goodness, I thought that said something else. Actually, oh my goodness. It's okay, year 7 deserve to be lied to. I thought you said something else. I'm going to move on swiftly. A strong acid, holy moly. The word strong means fully ionized. Stroke, or if you prefer, dissociated. What does that mean? It means that if I take a beaker of water and I put in it 5 HCl, I'm actually going to draw it with their bonds as well. 5 HCl molecules. If I add 5 moles of HCl, I take 5 moles, that's a lot of molecules, 6 times 6.022 times 10 to the 23. I add these to water, and what will all of them do? Every single one of them, fully ionized. They will all split apart. Every single one of them. Without fail. No fail here, folks. Every one splits up. That's what strong means. Yeah, it doesn't just mean split. It means all of them split, fully ionized or dissociated. Every underline, every molecule splits up, splits apart, fully ionized, splits apart. Okay, so what does weak mean? Are weak bases reversible? Yes, they are. Weak acids are too. So here's what weak now means. Question. Weak acid. I'm just going to focus on the acid bit because it applies, of course, straight to the other one anyway. Weak acid dissociation or ionization. Weak acid. What did I write for the last one? A strong acid. A weak acid. A weak acid. Let's start that again. A weak acid. ... Partially. I don't like that name, I really like that. Partially ionizes, stroke dissociates. So what does this mean? It means in the picture is different. I have my water. By the way, HF is weak. If I add my 5 moles of HF to the water. I add this to it. I add all of them to water, every one of them. But here's now the weird thing. Not all of them splits up. So one does, but the others remain intact. And here's, by the way, and this is about to get a whole lot more complicated. So would you agree 1 in 5 has separated? Yeah, does everyone get that? Only 1 in 5. Do you want to know what the real numbers are? In reality, do you know what? And I hate making up numbers. Okay. Hydrofluoric acid Ka value. Right, just so you know, this is part of A-level chemistry. The Ka value represents the how much dissociation there is, and it's 6.6 times 10 to the minus 4. Right, so 0.000616. Right, how do you get that to 1? So to get that to the number 1, I just divide 1 divided by 6. Was it 16? 6.6. Sorry. 6.6. And I don't like 6.6 exponential minus 4. Shift eng. 3 zeros, that's correct. Yeah. So 1 divided by answer. Right. So for hydrofluoric acid, 1 in 1,515 molecules split up. That's the reality, folks. Oh my God, that whole unit based on Ka. Yeah. Guys, do you know what? I love doing the extra stuff with you guys, and I will happily teach you all this stuff if I want to. Yeah, a whole unit based on Ka for dissociation. It's equilibriums in acid-base theory, but it just shows you how many molecules split up. 1 in 1,500 molecules split up. Now here's the extra bit. Now, guys, that's all you need to know. Can I just point out that there ends my lesson. That's it. That is all you need to know. A weak acid is partially ionized in water. That's it. I am done with my lesson. In water. I'll put in water. In water. It's French for water, if you don't know. So that's it for my lesson. But, you know what? I know you guys, and I know you guys will. So we now understand, we know the definitions for strong and weak. So strong, fully ionized, or dissociated, whichever you feel more comfortable with. Fully ionized in water, all split up. Weak, partially ionized in water. Yeah? So that brings me to the end of my lesson, but I'm just going to do a little bit more, just a tiny weeny bit, because I want to explain to you the reversible thing. So, okay, here's what's happening. I'm just going to draw the 5 up here, 5 HFs up here. So, in what's happening, and here's the water. When these go into, all of them go into the water. All of them do. Yeah? And when they drop into the water, they accept if you use either ionized or dissociated, right? Yes, absolutely, Atia. You can say either, whichever one you prefer. As long as I have to teach you both in case they give you the word and you have to understand what it means. But you can write down whichever one you prefer. We know now when this goes into water, one of them will split up into its ions and the others won't. The others will remain attached. But here's the really, really bizarre bit. This is the bit that you've got to try and get your head around. Here's the thing. The reaction is reversible. So moments later, what will happen is that these two will come back together. But this one would now split up. So at any given time, that one hasn't changed, that one hasn't changed. At any given time, only 1 in 1,515 is actually split up. Moments later, it comes back together. The equation is reversible, and this one now splits up. All that's happening is that they are constantly breaking apart and going back together. All the time, never ending. Hence why you have HF in equilibrium, with a reversible reaction between these two. And we will have 1,515 on that side and get 1 and 1 of that. Yeah, that's how far the equilibrium lies to that side. This is very, very weak. Now, okay, and now I'm using HF as the example. I know, by the way, I know that the lesson has come to an end. If you wish to leave year 10, you can. Yeah, if you want to leave, be more than welcome. I've actually been told that I'm only allowed to give you guys 50 minutes, but I'm just going to keep going. If you want to leave, please just say goodbye on the chat, and that's it. It'd be nice just to hear you guys say goodbye before you leave me. So let's look at somebody all of you recognize and know. Let's look at vinegar. Everyone in this room knows vinegar. You guys have all had it on your fish and chips, or you've added rice vinegar to your sushi. Everyone knows this molecule. Now, the thing is, you might not know what it actually looks like, and it looks like this. This is vinegar. Now, vinegar is a common name, and this is called ethan, for those who remember their year 9 chemistry, eth, which literally translates to 2 carbons. Next, an, which translates to carbon-carbon single bond. Well done, Lara. And oic acid for the ending. That structure there tells me it's an acid. Okay, so ethanoic acid is a weak acid, and you know this because you guys can eat it. And it doesn't, you'd never put hydrochloric acid in your mouth. It'll dissolve your teeth. But vinegar, everyone's okay with it. Hell, I often ask my year 7s if anybody's ever drank it, and they say, ethanoic acid. Dom, that's actually really good. Oh, no wonder he's so sour all the time. That's so funny. So what's happening to the ethanoic acid is when it goes into water, one of the H's, the special H, breaks away. It's very special. It's different to all the rest. And you put it into water, add to water, and it will split, and it will form this. There's the minus charge, and there is my H+. So the question is, if this here is acid, and this acid is dangerous, it's not just dangerous, it's corrosive, dissolves flesh and bones. Yeah? So why can you drink vinegar? Because to get one of these, you have 50,000 of these. Only 1 in 50,000 falls apart. Now, the way I now talk about how this is now, vinegar is not dangerous. Vinegar is safe. Well, why? Imagine you own a castle. Imagine you own a castle. I'm drawing, there you go. I'm drawing Zach's castle. This is Zach's castle. And here's Zach. Hey, Zach, you still there? I bet he's left. 1 stroke, 50,000 to die. Oh, yeah. Oh, look at helping, giving me the real number. Oh, did you just do the Ka value for ethanoic acid is 1.7 times 10 to the minus 5, and then did 1 divided by that number? You didn't do that. 1 divided 1.7 exponential minus 5. No, Oh my God, you actually did. How Ping, I love you. You're awesome. It's boss. Where's Zach? Zach! I would stay in there. Right, Zach. Let's give Zach a smiley face. Yeah. Now, Zach, of course, is the king. It's King Zach. Everyone knows this. This is King Zach. It's King Zach. So King Zach owns his mountain. And what we're now going to do is we're now going to attack Zach with acids. Hail King Zach. Exactly. So if you add HCl to this, here's the problem. Yeah. 1 drop of hydrochloric acid contains millions of HCl's, which means they all split up in water. And what now happens is that every H plus charges all at the same time, and Zach can't fend them off. He's sitting there with his bow and arrow. With his bow and arrow, he's going to shoot them all. Yeah, as they run in, these are the H plus people. Yeah, these are the H plus people. Like they're just H pluses on the ground. They're all going to run in at once. All hail Zach, that shall be king. So strong acids, with strong acids, they all attack at once. All attack at once. And it's very difficult for the body to respond. Why doesn't the king have an army? Yeah, the king, yeah, but there's only one of you. And when you're drinking, imagine you're drinking a bottle of acid. That acid has millions in their army, but there's only one of you at you. That's why. But if it's weak, what would happen if we swapped HCl for a weak acid? What would happen? Oh, go away. It won't give me my keyboard. Ah, I want the keyboard. Give me the keyboard. Yes, go. If we now swap this for a weak acid, he only needs helping to protect him. If we now swap it for vinegar, I'm going to make my pen fatter. If we now swap it for vinegar, now vinegar is weak. It's a weakling. It's a weak acid. Now, he has an army too. He has an army as well. But what he's going to do, and he's got an army of 50,000 people. 50, I'm not going to draw them all, it'd take me ages. 50,000. But here's the really clever bit. Only one attacks at a time, because only one splits up. And there's my man who now runs in towards Zach, and Zach shoots him. So after he's been eliminated by Zach, the next one will go. Yeah, the next one splits up. And Zach, of course, will defend himself, and he'll shoot him. So what you realize, the chosen one, I know, right? The reason why you can drink weak acids is because they're not all attacking you at once. And your body can cope with it, and it can neutralize them as they're arriving. That's what gives it the sour taste. And so, kind of neat, I guess. I'll go back. I'll end the lesson. I've already overshot by 10 minutes. I'm so sorry, folks. Year 10. I'm done. We're done. Zach, thank you for playing such a vital part in my lesson today. It's been amazing. It's been great. Guys, I miss you all so much. I hope you've all had a really lovely long weekend. It's so nice to have you all back. And I will see you guys tomorrow. Have a nice rest of your day. I feel like drinking. No, Libby, please don't. It's not very nice. It's also not very good for your teeth. Thanks, Senor Duncan. You're very welcome, Amani. Very welcome. You need to thank King Zach, obviously. Wait, so even though HF is weak, can it destroy bones? Ah, okay, Atia. Okay, so HF is a very, very weak acid. 1 in 1,500 breakup. Now, it's also very small. What that means is if you spill it on your skin, because it's weak, it won't burn you the way that you'd imagine an acid would. In fact, you'd feel nothing at all, like spilling vinegar on you. But here's what it will do, is it's so small it will pass through your skin, and it will dissolve your bones from the inside out very slowly. and very painfully. It's not a nice way to go. It is corrosive indeed, but HF is a very standout acid because it loves bones. It loves being called what's called calcified. Yeah, it's just loves calcium, loves to eat bones, but it won't actually hurt your skin at all. It's like vinegar. You spill vinegar on your skin, unless you're in a cut, you won't even feel it. Yeah, but really, by the way, most people if you actually spill HF on you, you don't die from the corrosive action of the acid. What happens is it eats your bones become sharp like blades inside you, and then they cut your blood vessels open and you die from internal bleeding. Not very nice. Guys, I will leave you guys be. Have a nice evening. It is from the Harry Potter scene. Yeah, but way more gruesome. Way more gruesome. Guys, have a nice evening. See you later, folks. Take care. Bye. See you later.